Hello, welcome back to Fat Mama Physics. This is episode 6 of the Topic D1 series. This video and the next one will feature application of the equipotential line lesson, and the key is the relationship between gravitational field and gravitational potential, featuring Lulu Pig and our beloved singer, Shen Shen. The two examples of the two videos will be heavily graph focused. This first video is to look at the gravitational field and potential inside the surface of the Earth. Since most of the time we'd be dealing with the surface, gravitational field on the surface of the Earth, or far away into space, we've never actually looked at what it would be like inside the Earth. That's where this picture here comes into play, where if you're looking at the gravitational field inside the Earth, whatever causes that gravitational field, or the mass that is affecting the gravitational field, is only a small portion or fraction of the Earth. Imagining that the Earth is made up of all these layers, as you learned in Geo. There is the crust, the mantle, the core. So at the inside of the Earth, all of these outer layers are not going to have an effect on the gravitational field here on the surface, as you see where my mouse is pointing. So we're not actually going to do some fancy derivations here, but we just want to reapply the understanding of slope on a gravitational potential graph gives us the gravitational field. So this concept of the slope. For some points of reference, we'll say that the entire radius, I'm just using Earth as an example, is capital R. And from the center of the Earth to this inside of the Earth, this arbitrary distance within the surface or the crust of the Earth, maybe it's a core or whatever, we'll call this small r. Here are two graphs. Here we have the gravitational field versus distance away from the center of mass. Our big R is of course, the radius of the Earth. So you see it undergoes 1 over r squared, which is your inverse square law, as we've studied before. And then below this r, which is underneath the surface of the Earth. Looks like GS is the gravitational field at the surface of the Earth, and then we will see how it decreases as we go towards the center of the Earth. Here we have a graph of the gravitational potential. This is just an arbitrary spherical mass, but I wanted the graph for the shape. So what we want to do is using a bit of derivations just to show us how this gravitational potential graph would look like, knowing that, and also from the fact that why we see a straight line, a linear relationship between gravitational field and radius inside the surface of the Earth. So before we are able to show this gravitational field portion, one thing we have to assume is that we have a uniform dense mass sphere for the Earth. So that means that no matter if you're talking about the inner core of the Earth, outer core, mantle, crest, we assume uniform density. So maybe it's important to find the density of the Earth first. We know that density is the mass of the Earth divided by its total volume, which is going to be constant regardless if you're looking at the core or somewhere further out. The mass of the Earth I'm going to label as M, just capital M, because there's no other mass. Volume, the equation for the volume of a sphere, as you can find your formula sheet or memorize it because you use it enough, 4 over 3 pi r cubed. And this big R is the full radius of the Earth. Now, if we want to obtain the gravitational field of, say, this small piece of mass at the center of the Earth, then we need that mass and not the mass of the entire Earth. And so to find the mass, we know that the density is consistent. We just have to take the density, multiply it by whatever volume is there to get the mass. So essentially we're just taking density, the definition of density, and just flipping the equation to get mass as density times volume of your new sphere. The density, we know it is your big M over 4 over 3 pi r cubed, capital R cubed. And the new volume is also a sphere. So the equation for a sphere is 4 over 3 pi, but this time the r is a small r according to this diagram, which is just a radius from the center of the Earth to wherever that piece of mass that we're trying to find for its gravitational field. So we get this. As the new mass, a few things do cancel, including 4 over 3 pi. And you know what? Maybe you might try to do the rest of this, because now you know the mass, right? And so the mass then simplifies to m, small r cubed, over the radius of the Earth cubed. Now that we have the new mass, we can then substitute this new mass into the gravitational field equation. So then we get big G, and from putting in the mass, the new mass, which is m small r cubed over big R cubed. And don't forget, there's also the r squared as part of the original definition of gravitational field. And the reason why it's small r is because we're trying to find a gravitational field somewhere in the middle of the Earth. So a few things can now cancel, including this r squared with 2 of the r's on the top. So we'll just end up with 1 r on the top. So your gravitational field then simplifies to big G, big M, 1 of the small r's, okay, divided by the radius of the Earth cubed. Notice that big G, big M, and r cubed, this is a constant, because mass of the Earth is always constant, the radius of the Earth is constant, and the only thing here that varies depending on what you want, or which part of the core of the Earth you want, is the small r. And notice it's only to the exponent of 1, meaning that this is going to give us a linear relationship between G and r. And this is exactly what we see on this graph over here, where r, which is our x variable, as small r increases, the gravitational field increases linearly inside the Earth, planet, or outside the surface of the planet. Okay. Okay, so now we can ultimately answer this question: what should the rest of this graph look like on the gravitational potential versus distance graph? Going back to the definition of gravitational field, this is negative, taking the negative derivative of the G, which is the gravitational potential, over, we're kind of looking at how it slopes, how it slants over space. So remember, as the lines get closer together, it is steeper. As these equipotential lines get further away, there's more space for the gravitational potential to decrease over space. So essentially, I need this line to look a certain way, so that if I take the slope of it, it's going to give me a linear line, a straight line. So one of the things that we can conclude here is that this line cannot be straight, because if you take the slope of a straight line, you're just going to get a constant. And that's not true, because we need a linear relationship that slopes upward. And if you haven't taken calculus, which I'm sorry, I put a lot of emphasis on calculus, but if you, even if you don't take calculus, you can still reason that you're needing some sort of a curve on this graph, so that as you continuously take the slope should increase. Therefore, gravitational field continues to increase. Starting off, so kind of working backwards here, if we take a look at the gravitational field, it starts off at 0, meaning the slope on the gravitational potential graph should be 0. Slope should be 0 in the beginning. We know that the slope is 0 when we have something that looks like this. So if I extend this line down here, and we know that this graph is going to keep going down, but we don't know how it's going to end up. It could be, we ruled out it's not going to be a straight line like that, okay? But it should start off flat, because we need a slope of 0 where this starts off. Then the slope should steadily increase. So those slope starts off small, and it gets bigger and bigger and bigger. So it starts off small, small, bigger, 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 and hey, now what you have here is a curve. Let's make that curve look a little better. And if I wanted to link it to the rest of the graph, then it looks like this curve. It looks kind of parabolic. It's kind of like, probably will make you think of kinematics when we talked about the slope of a graph, a curved graph, meaning that it accelerates. Slope is 0, slope is positive, and slope is continuously increasing. So that's what we want the gravitational field to look like. If you take calculus, then you probably know that it is probably some sort of a square, maybe-ish relationship. If you get a linear line. Really, the emphasis on this video is reapplying the concept of the gravitational field with respect to gravitational potential. So hopefully we have hope that expanded our thinking a little bit. The emphasis of this video should not be that high in the scope of this entire unit, but it's just a cool way to visualize graphs and gravitational field. Otherwise, thank you for watching, and Fat Mama Physics signing out.